Thank you very much, and thank you all for coming to our symposium. It's fantastic to see everyone face to face, old friends, new friends. Also, there are a lot of people joining online as well. So I also thank your participation, and it'll be an exciting 2 days, and also various meetings for the week ahead. So again, we appreciate your participation. There's going to be lots of exciting talks, and hope to kick it off with something that's rather controversial to keep you awake, okay, to wake you up. So just to start off, the Fugaku, it's been in operation for almost 2 years. We've been very successful in so-called application first design. We got something close to 70x speed up on our key applications. Also, we were awarded with benchmarking accolades, not just on one benchmark, but across many benchmarks, which was very important because you don't want to build a machine that's only good on LIMPAC. Also, there's been very important results, which were also accoladed with Gordon Bell Prizes last year in 2021 with our COVID infection simulation, and also last year jointly with US and Europe. And then there's been really innovative applications that we had a real-time, very detailed forecast done for the Tokyo Olympics, which were basically not only forecasts made, but also the results distributed in real time to smartphones. Unfortunately, Tokyo Olympics didn't have any spectators, so it wasn't as expected, but still was a very big experiment, saying HPC is no longer just crunching big iron. I'll get to that later on. So the number of users have been rising. This is somewhat an older figure. We're getting a lot more users. But what's important is not just the number of users, but the recent survey showed, and this is the results, 2 independent survey results from 2 different organizations that showed that not only Fugaku is being used for basic research, for pure academic research, but also 60% of the Fugaku projects involve some sort of industry presence. That it could be someone who's industry joining basic research. It's not just pure industry research. We have 15% allocation for that, but it goes to show that even from the onset, when let's say universities and national labs do the research, they already involve industrial users for very rapid translation of the results over to the industry. Okay, so this was a lot higher percentage than we saw for K-computer or any other supercomputers we have had in Japan. So there's a lot of good attention being paid to Fugaku with respect to that being a very credible infrastructure to move the society forward, for the so-called Society 5.0. Now, with the energy crisis that happened in 2022 with the events we all know, and that we're all suffering, those who share my similar roles with the computing centers must already or are starting to suffer the pains of rising energy costs. And in fact, it was fairly serious in Japan too. And we had to do everything to save power because there are a lot of power-saving features in Fugaku that we had not turned on for operational reasons, safety reasons. But we became adventurous and basically carefully but very successfully turned most of the features on. And also we asked the users to use the Fugaku in the most power-efficient mode without sacrificing the runtime. Because if they sacrifice the runtime or time solution, then actually that involves loss of opportunity and actually involves more energy. So we don't want the users to slow down their applications. But even so, Fugaku offers user power modes that would control the power on the application. So we ask the users to test their applications in available power modes and pick the one which has the same runtime as their normal operation, but will give them the best power. because the users get feedback on how much power and energy they used. And even so, we had to shut down like 30% because it was already mid-year. So we had to shut down like 30% for the resources over the summer for like 4 months. Then we made recovery. We were able to turn everything back on. But the fortunate news is that because of this, we also gained additional experiences, operational experiences in controlling the power. So before and after the crisis, well, still in the crisis, but before and after this event, we are managing to save additional 10 to 15% power on average over the production, which is, for a large machine like Fugaku, which uses about 16 to 18 megawatts of power for the machine alone, and cooling, including cooling, we use more than 20 megawatts. That's a huge saving. Now, Fugaku has 160,000, I said 16 megawatts, that seems a lot. But remember, Fugaku has 160,000 nodes. That amounts to less than 100 watts per node. And each node can be as powerful as, let's say, your Xeon CPU node with 2-socket node. You benchmark, we get various results, but let's say they're about the same. But if you have a Xeon server, that's like 300, 400 watts, while we're operating at 100 watts. So this also goes to show that the metrics like Agree 500 is pretty much a nonsense, because it's not what counts. What really counts is the real power you use during the operations. And 100 watts is really low. And you can get the real-time account of this. There's a public status page, and you can get all the status of Fugaku, all the 160,000 nodes in real time, and you can also get archival data. And it's really fun to poke around this web page. So if you can't remember this URL, just do a Google search, Fugaku status, and you'll hit this page. And it's really interesting to poke around. In fact, we'll be working with Oak Ridge to actually work with them to extend this platform so that these platforms can be shared, so we get operational status of Frontier at the same time. In fact, we can get very similar data, hopefully. So, but then I get to more of a concerning part, because when you look at the latest machine that DOE has put up, which is a great machine, Frontier is by no means a slouch or anything. It's a state of the art. It's a fantastic machine, and I think there will be lots of good science being done. That will be done on the machine. It's already being demonstrated in its early production. But then when you look at the numbers, there are some numbers where Fugaku is better. There are some numbers where Frontier is better. On Limpac, of course, Frontier is better. But when you look at the machines holistically, then you find that these machines are pretty much, pretty much matched up. And it's very likely that in real production, on the average, these two machines will perform very similarly. Again, some faster on Frontier, some faster on Fugaku, because we have, for example, more memory bandwidth, while Frontier has more flops. And we have more memory and so forth. We have faster network. They have more I/O. And so and by and large, these should match up pretty well. Now, that's where the concern is. Frontier is about 2 to 3 years after Fugaku, okay, as technology-wise. In fact, when we look at the latest chips from our major vendors, like AMD, with Frontier is built with, or the NVIDIA H100 or Ponte Vecchio, these are early numbers, so we have to confirm these in actual production. These are just catalog numbers. But if they are, by experience, and we're getting some data from sharing some data with Frontier, that when we look at these numbers, okay, there's not much progress that's been made since Fugaku have been launched. Because, for example, a lot of the dominant, as I will allude to later, the dominant workload for these machines are largely memory bound. About 70% of the applications are memory bound. What will count, as I said in the earlier slide, is bytes movable per watt. Because wattage basically limits the size of the machine that we can operate. And then the bandwidth, how much bandwidth you get. will be for each watt will become the performance, will become the dominating performance metric. Have we made advances with these latest, greatest GPUs? No, not at all. In fact, if we believe the catalog numbers, in fact, they have decreased over A-squared effects. Now, it's very likely for production, these numbers will be slightly better, but even so, it'll be like parity. And that's why we say, or one of the reasons we say frontier performance will be, by and large, for real apps, will be about the same as Fugaku, because the metrics and the power will be very similar. Because the power will be similar and the numbers are similar. But it's like 3 years. Okay? So moving forward, and we achieved sort of exascale, but moving forward, these are very concerning numbers because we're not making progress here. So thus, so a group of us are getting we're doing lots of basic research at R-CCS. In fact, a group of us got together, myself, Thorsten Hoffler, who is a co-award winner last year at SC. I was fortunate enough to be given the Cray Award. Thorsten became the youngest person to be to receive the Fernbach Award by a few months, actually. So he'll probably surpass me in various respects. One of the best we have of his generation, and other people who are my Skunkworks team at R-CCS, really bright, young, super young, bright guys who are become team leaders and so forth, kind of sitting in the audience. So and many of our friends who helped out. And the paper we've written was, which has been kind of going around, and if you haven't read it, it'd be very nice if you can read it. It's still under review, but the first preprint is an archive. It is what we call the myths and legends in high performance computing. And it was a really fun paper to write and read. So we came up, since it was Christmas time, we came up with the 12 myths of HPC, just like the old song, 12, like 12 days in Christmas. So there are various myths that we said, like, our favorite, everyone's favorite, like quantum computing will take over. If you believe the popular press, still a lot of people are advocating, press is advocating this. And of course, which is total nonsense, but still quantum is important. Very, very important. All the way down to something like HPC will be subsumed by the cloud. So I don't have time to go over all of the myths. In fact, again, I will advise you to not only read the paper, but join in on these lively, active discussions. I think over the course of the year, we'll have panels and hallway conversations about any of these subject matters. But again, these are some of the things we need to consider as we move forward. Okay, so I'll cover some of the myths, and this will also reveal our thinking towards what should be the next generation, how we should think about the next generation machine. So we go with myth number 6, which is we will soon run at X zettascale. Okay, or the myth 9, so very associated with myth 9, says applications continue to improve even on stagnating hardware due to the end of Moore's law. So is this a myth, or is it going to be true? Okay, so if you read the paper, primarily Jan Donke, who is one of our who's a team leader of a high performance performance modeling and analytics and everything else team. So we've done a very careful analysis of the extrapolations of the trends and also looking at technologies largely bound by Guilford per watt and so forth with respect to the prospective rise of the FP64 arithmetic. So one of our partner vendors, not putting them down by any means, but has a very speculative number that says we'll reach X zettascale by 2032. Even we don't know even if it's a credible goal. But it says even with the best our knowledge is that will not likely be the case. We'll probably reach, if we have any hope, we may be reaching a zettascale by 2038 if the technology still continues to push in the way that we have been used to. And of course, that's going to be hard and harder every day. Okay, so that's that. But is there a way to reach zettascale, effective zettascale performance? And of course, for many application areas, we believe it would be. So it's not a credible goal to say we reach zettascale in LIMPAC, because again, even right now, LIMPAC, reaching whatever performance in LIMPAC is a pretty useless goal. But what we really want to do is to increase the performances of our applications. So if we mean zettascale, it's at like 1,000, right now we're at exascale, right? So can we effectively improve the performances of our applications by a factor of 1,000 while preserving the accuracy and other properties that we want to preserve of the applications? So this is work recently done by Tsuyoshi Ichimura's team, the Earthquakes Institute at the University of Tokyo. This paper won the Best Paper Award at HPC Asia, and he had a very associated work on certainly quantification, became the Gordon Bell finalist at SC22. And so I won't go into the details of the work, but just to show you what kind of stuff they achieved. Oops. Oh, there's supposed to be animation here. Oh, okay. So because the animation quite doesn't work, I'll just tell you verbally. So what they want to do is to do this earthquake simulation, but as a holistically. So everything from earthquake being generated with some rupture in the earth crust, and then the waves propagating to the surface and destroying the city. They want to do a very holistic simulation. For this, they projected that they would want to simulate the whole city. They need something like a 10 exascale performance. Okay, and given that Fugaku is like half exaflop or exaflop, depending on the precision, but still we're like factor 10 to 20 away. So what they had done is, so we have the time 42x improvement over the K computer, which was a 10 petaflop machine. Of course, back in 2014, they had a Gordon Bell finalist paper, which basically was a state-of-the-art solver for this, and they had achieved a certain performance on the K computer. And again, the application wasn't a slouch. It was a very, very state-of-the-art applications. But from that, they have made advances, not only using equation-based modeling, traditional PDE solver, that they have innovated, and they made some innovations for that, but also they use data science approach, which is not to say they use this entire proxy. They still preserve the accuracy. So they got the same result as if they had been computing with just a PDE solver. So no loss in accuracy here. But because of this combined approach, data science, which is not only entirely AI-driven, but it's very similar methodology, they were able to get 25 times speed up of the application. So the combined speed up over K with the hardware advances made with Fugaku and the advances made with Solver, they were able to attain a 1,000 times speed up, which is effective 10 exascale performance. Okay, and then they were able to get sufficient resolution to tackle the problem they wanted to do, is to do the first principle simulations from the earthquake source all the way to destruction of buildings. Okay, so in fact, to give you some numbers, they're still solving a 1.2 trillion degrees of freedom problem, which is huge. And there were like 19 trillion component data set, these huge numbers. And but they were able to solve this effectively. And unless you have a 10 exascale machine, you can't solve these problems. So moving forward, can we reach zettascale performance effectively? And that's more of a goal, rather than to say we'll build just build hardware. And so let's say we achieve 20 exaflop hardware advance, which may or may not be possible, but we're studying something like that, largely being more memory bound, but something of the range. And if we can get a 50x, similar, like more than 2 orders of magnitude speed up using physics and data and AI algorithms, we can get effective zettascale. Okay, and this again, this is more of an application-first philosophy. And what we develop are not just hardware. We develop the algorithms and software. But how do we develop these algorithms and software and make it easy for the application teams to do this? Well, that's going to be the most important problem. Okay. Now, and also, there are some debates with respect to whether we can expect this type of continued speed up of application with algorithmic innovations. So David Keyes and did some studies with Tom Schultes and so forth with regards to the advances in the various algorithms and various types of application space. And certainly there have been advances made that have added to our hardware advances and thus allowed us to accelerate our applications more than what we have accelerated in hardware. Now, can we continue this trend? That's something we really need to do research on. So that'll be one of the most important studies moving forward. Can we do co-design such that the algorithms, the new types of algorithms combining things like, the new physics, not only new physics, but also combining this AI, data-driven computation, and also combining them so that we would not be losing precision or quantify the uncertainties to the extent that we will continue this upward upswing trend in performance. Yeah. Okay, then what kind of hardware do we run on? Okay, so the myth number 4 is to say everything will run on some accelerator. And the associated myth is everything will be deep learning. Okay, we'll get to that. And we'll get to that because earlier we wrote this paper again with a group of people, some people that common with the previous paper. This was a paper. The author was Jens Duncan, but we had a whole bunch of other people like Mohammed Wahib and Alex Droid and many other people, and some people from other institutions. So this paper really studied whether the dense linear algebra, aka LIMPAC, is useful. Okay. And then, of course, the foregone conclusion is if we look across a range of applications, these are DOE ECP apps, spec weekends, benchmarks, spec, not just a spec CPU, but spec OMP, MPI, and so forth. We find, and we not only looked at the calls to BLAS routines, because that will not be sufficient. In fact, we did cloud sourcing, the student teams, for them to look at the codes in detail and identify patterns that look like dense linear algebra. And we've had teams, red team and blue team, to actually not only to have one team look at it, but have multiple teams look at it to make sure that we don't miss these patterns. Okay, so that's a very detailed study. So these numbers are fairly trustworthy. So this says for traditional HPC app workloads, only very, very small number of applications have these dense linear algebra operations. So again, LIMPAC is not a very useful metric because of this. Some of the deep learning kernels do have dense arithmetic. But usually, as we know, these are usually done with low precision, FP32 or below. So having FP64 dense linear algebra capability is not very meaningful. Only meaningful for very small number of applications. This is LIMPAC here. Some where there's a little bar. These are usually first principle molecular orbital calculations, where they do have high precision requirements. So, but what about the entire workload? So we created a simulated workload and then try to see what will be the speed up if we had infinite a matrix. If the FP64 dense linear algebra calculations were sped up to infinity, right? So what will be? So this is like asymptotic test. And for the K's workload, we got 7% speed up for the entire workload. For Argonne, at the time, it was 10%. And if we have increased presence of machine learning workloads, combining machine learning also some of the physics calculations, we believe it could be up to 32%, but this also includes low precision arithmetic. IP64 is going to be much lower. Okay. So in fact, what's important, as we all know, is increasing the bandwidth, because this is where most of the, I'm sorry for the Japanese, but this is where most of the application limitations will come from. So uplifting the roofline is going to be the really important thing. In fact, it's really important to identify the compute patterns of the kernels and see what they are, and then to see how much of the occupancy they have and what would be the potential speed up, and then think about what kind of machine we can build. So some applications are compute bound, some are bandwidth bound, some are latency bound. Okay, this is a very rough coarse-grained analysis, force and real analysis that we're doing. We are doing much more detailed analysis. But when you look at how the machines have evolved over the years to cope with these types of workloads, in the old days we had classic vector machines, which basically largely dealt with the bandwidth compute to some extent. So there's like a classic vector machines of Cray and also things like the Earth simulator. Then the COTS CPU machines became prevalent in the late 90s and early 2000s. And the expectation was, because each CPU would be weak in all aspects, but combining them, making them massively parallel, will have enough performance across the kernels to cover, to basically cover all the application space. Then the GPUs came about, and I've written a paper 2008 at VECPAR with a VECPAR meeting, which was which I pointed out that these GPUs are basically resurrections of vector machines, but in commodity space. So so then the GPUs came about, but also GPUs, because the graphics requirements also came with to some extent accidentally came with lots of compute units too. So so the GPU machines that have been built since then, including machine I built like Tsubame and ABCI, and machine like Summit, Frontier, Aurora, so forth, basically covers these two spaces with GPUs where the latency bound is covered with CPU. But then you can think of other combinations. For example, A2FX is almost like this, but it's a little different, because what we try to do is to bring in the GPU features back into the CPU with very large vectors and fast memory. So it's a little different than COTS. Oops. But then you can have other combinations where you can think of the bandwidth-bound applications being covered by CPUs, whereas a dense linear algebra just being covered by GPUs or matrix engines, or both covered, because we find that with applications of very complicated boundary conditions and so forth, it's very difficult to program on a GPU. So you want CPUs to cover those for some of the codes, whereas use the GPUs for dense linear algebra, or you can think of other combinations too. In fact, one of the latest combinations we're looking at is we have a more specific processor for strong scaling to go beyond CPUs. And we'd be using CPUs for bandwidth bound, and we do compute bound, and also compute bound for strong scaling processor. So it's these two combinations that we run on future whatever GPUs or whatnot, whereas the bandwidth bound we covered by CPU, which is a very different combination than what we have today. Okay, so these types of analysis is really important, and then do the analysis on that's fine, but then can we get speed up of immense bandwidth increase with the future technologies, and if we do, what would be potential speed up that we can expect? So this is one paper we have recently written. I think it's in submission right now, in that we try to analyze this using trying to create a hypothetical processor circa 2028, 29. That's an extrapolation of what we have with A2FX, and then do some groundwork experiments using either that or other CPUs, and then try to think about how much these new CPUs in the 2030s will be, what kind of power we'll be using, how much bandwidth we can get, and also what's the performance expectations. So one thing we looked at is to do some early experiments using the Milan X, which is an AMD processor. And one trait of Milan is has a 3D, what they AMD call the 3D V cache, which dramatically increases the capacity of the level 3 cache, which of course is supposed to give us some speed up. But if you look at the numbers from AMD, this is the graph they will show you, which says, well, you get like mediocre performance gains. You get like, some apps you don't get any performance gain at all. Sometimes you may lose performance, and for the performance gains you may get like 20%, 40%. Okay, but when you think about this, these are workloads that basically blow the L3 cache capacity. The Vcache in Milan-X has like almost like 2 terabytes per second memory bandwidth, which is equivalent to HBM bandwidth on GPUs, or or potentially on some of the CPUs like FX or the Sapphire Rapids that Intel came out with. So this is a graph that shows what happens when you try the problem with different sizes, and you see here the peak is at 3x, more than 3x performance, and this is the performance when you maximize the amount, the capacity used, but per core, however, still staying within the 3D cache. Okay, then you get 3 times performance. Okay, and this is, instead of a 300 cubic, this is 150 cubic, which is 1/8 the problem size you have on the mini FE. So, and for the future processor, think about, okay, we confine this in the SRAM. But then for this generation, we split it up. So you need 8 processors to get back to the problem size of 300 cubic. Then what kind of speed up do you get? Well, you get 3 times speed up because of the capacity, because the bandwidth increase. You get 8 times speed up because of the parallelism. So you get 24 times speed up, okay, combined. Of course, there will be some increase in power as a result, but of course, we know some ways to control that. So theoretically, if we get dramatic increase along with the parallelism, because we will not be increasing the core, the size of the cores, we'll get dramatic speed up out of these future CPUs. So we created several strawman CPUs, we call it LARC, and then try to look at what would be the various hardware parameters. We have a few gigabytes of stack L2 cache, which are SRAMs, and more details. I would encourage you to read our paper, which is on arXiv. And then we try to do some analysis with respect to what kind of speed up we get out of these applications. In fact, we ran a whole bunch of simulators, and we got up to like factor 10 speed up, even on existing codes. Of course, for compute-bound workloads, we only get speed up with respect to per core. With respect to the number of cores, things proportional to number of cores, and for bandwidth-bound applications, we get that as well. So, so the key is to look at the workloads, analyze the workloads, and then think about what would be the right proper architecture moving forward, and what kind of innovations we need to create. And later on in the feasibility study talks that we have, we may be able to present you with some of the results, although a lot of the details are still under NDA. So, okay, and this kind of workload analysis also goes for the potential myth like everything will be deep learning. Of course, we don't. This is not to really say bad things about AI. In fact, AI is wonderful. It's a wonderful technology, and of course, the future is to combine first principle based physics simulation and the empirical AI-based predictions, and then also combine that with have a tight coupling with big data instrumentation with techniques like data assimilation, and that's definitely going to be the future of HPC, okay? And in fact, HPC future for the infrastructure. But it's a little. But when you try to analyze, there's been several phases of AI over the years, and right now a lot of results are being obtained by what we might call AI 4.0, which is really HPC for AI. HPC enabling massive scaling of deep learning training so that we get new things, innovative, groundbreaking results, such as things like, GPT-3 or stable diffusion and even generative AIs, like that. So lots of innovations which will probably change society. And here, the supercomputer is used as infrastructure for training, for covering a training workload. So majority of the workload on the machine will be on training. So any machine that Google has built with Tensor Core, with the TPUs, any machine like NVIDIA had built, and so forth, they're really focused on training, accelerating training, and the majority of the workload will be training workloads. Okay, like training a GPT language model is a huge endeavor. The new generation of AI, what we might call AI 5.0, is more to do with combining the three. So we have the simulation component, and we have the AI component, we have the cyberspace, we have the physical space, and there's a cyber physical thing. And there will be various ways that simulations, first principle based simulations, and the AI will interact. Again, this is a wonderful thing. So the machine needs to cope with these these types of mixed workloads. However, so you got to run a variety of physics codes. You got to run a variety of AI codes. But that's different from saying you need a machine that covers both very well in terms of their compute capacity. Okay, that's a totally different thing. Okay, so there's a paper written by Shantanu Jha. Again, this is a fairly light read. And so for most, and practically, even at R-CCS and partners, practically all the application teams are using AI one way or another. I don't think there's many teams that don't use any AI techniques. Okay, so that's more of a standard. It's their standard toolbox. So use of AI is just prevalent. There's nothing surprising here. However, the use of the machine learning in most cases are things like surrogates or using AI to optimize. These are using inference capabilities. And we all know that inferencing is fairly lightweight. Okay? And there'll be minuscule workloads. In terms of capacity, there will be minuscule workloads compared to physics. There are some minor training workloads. For example, the popular usage, again, identified in this paper, and we all know this. Training the deep learning network using data synthesized physics simulation. That's a very typical thing. We have a wonderful case by Fujitsu that does this, and many others. There may be some real-time retraining, for example, doing some reinforcement training used to combine physics. But when we look at these workloads so far, again, the workload is dominated by the physics part and not by the AI part. Okay. So as much as you need to be able, the machine needs, in fact, you want the machine to be flexible because these ratios change all the time. So, and also a lot of these cases, they become IO bound because you got such a massive data coming out of physics. So training typically becomes IO bound, not by the compute capability. So right now, and this is numbers that some of our partners also have quoted, that for AI 5.0 type of workload, combined workload, we expect the deep learning part to be about maybe 10% or less of the entire capacity. But this is like rule of thumb. We need to confirm this. On the other hand, we need to have them to be really tightly coupled and flexible. So the current GPUs, or even running this on CPUs, like the GPU-CPU combination with very fast I/O, in fact, is a great combination. Things like Aurora, Frontier, or Lumi, there are great combinations because they're not using specialized AI hardware. Rather, the GPU can do anything. Right? It can do compute physics, it can compute AI. So we believe that specialized AI chips and machines are not very necessary for these types of machines. But of course, we need future work to confirm this assessment. And 3, extreme specialization, as we see in smartphones. So a lot of people proclaim that because of the end of Moore's law is approaching, we need to customize our hardware to fit the problem. And the instance of this is a smartphone chip, like we have an iPhone. But we have to remember that supercomputers are not iPhones, right? Smartphones. Because the one way we get speed up out of these machines is not accelerating the chips themselves. But what we have practiced since the days of, let's say, going back to the 1990s, when we started dealing with these, like the days of ASCII program, is basically parallelism, right? Or scaling. In fact, weak scaling. So unless we enable weak scaling, and a machine like Fugaku, we have 8 million CPU cores, so it's a massive weak scaling machine. So unless we can enable weak scaling, the speed up you get out of hardware specialization may be in factor 2 or 3. Okay? Weak scaling, we get millions. So which do you prefer? Okay, so that's the important thing. So, and also specialization leads to poor programming. So, things like CPUs and now GPUs have a very good software ecosystem. Okay, so that's good. But it becomes any sort of specialized hardware, you have to realize you have to incorporate it very well into your software stack, such that it does not become a hindrance to productivity. And again, the important thing is that performance is not only governed by Amdahl's law, which will give you a minor speed up. Okay, the major speed up comes from scaling, which is the weak scaling of the Gustafson's law. So if the strong scaling component hinders the weak scaling, then you don't want to do that. But will it? So this is a paper we recently wrote. This is one of the SIAM news article along the Jens, in which we did some rudimentary analysis as to how these two interact. In fact, these two laws, so-called laws, are very well related. But to just give you a cartoon intuitive understanding. So Amdahl's law is basically you have the non-accelerated part, you have the accelerated part, and this will shrink and shrink until you reach the asymptotic limit of infinite speed up of the acceleratable component. Okay, so this is a limit, and this was why Gordon Bell and Karp and those people questioned the validity of massively parallel machines back in 1986. Around 1980s, Gordon Bell was sort of on both sides, but he was curious, so thus he invented the Gordon Bell Prize. And then Gustafson and his team SNDIA won the first award by scaling the application by a factor of 400 in a 1,000 node N-cube machine. And thus the weak scaling revolution started. Now, weak scaling is where you're not going to shorten the time to solution, but rather you increase the problem size. And by increasing problem size, you basically get proportional performance increase because of this. Now, so what happens when we combine both? Then what happens is this accelerated part becomes smaller and smaller. Okay. So, but to achieve perfect weak scaling, this has to be perfectly matching, or they need to be perfectly independent. So thus, but if there is any synchronization, this part has to be totally synchronized with zero time asymptotically, which is of course impossible. So any overhead will kill your weak scaling performance. So that's why you don't want, so combining both are very difficult. And that is why it's no accident that every machine, so-called accelerated machine combining CPU and GPU, have homogeneous node configurations, and also that there's tight coupling, and and also dominant. Also, when you write your software, dominant processing will either be on the GPU or CPU. You don't combine them, because when you try to combine them, it becomes very hard to load balance. Okay, goes for any machine. Okay, that's all successful machines follow this pattern since the days of the inception of a GPU machine. Okay? So, and there's no way around it. Okay, I'm sorry, there's no way around it. So combining multiple domain-specific accelerators and try to utilize every one of them, it will be a daunting task when you try to scale. You try to use weak scaling in the millions. Okay? It's simply difficult. Why would you do something difficult when the problem is already hard? Okay? So these are the things that we consider when we're doing in conducting our feasibility study, but you get a lot of details of this later on. And hopefully by combining these ideas, we will be, we are right now in the feasibility study state, and then we'll go into the design phase and so forth. You get all the details of our plans. Hopefully this will pan out. And we'll have the next machine hopefully by 2030. And, we're giving it all the technological considerations like 3D stacking for high bandwidth, photonics, massive tiling, all the works to basically attain extremely high bandwidth. That's our key. Flops really doesn't matter. But we may have some customized processors to deal with strong scaling and some matrix codes or things like deep learning. But okay, this is balancing with the workload requirement. And we got fortunately our effort seems to be innovative enough to involve a lot of our usual suspects on the US side, like not just Fujitsu, but Intel, AMD, NVIDIA, HPE, and maybe ARM, and maybe some others. And of course, we got all the Japanese teams involved in software and applications too. Okay? But you hear more details about that later. So for my final moments, I'll spend by saying subsumed by cloud. So there's another recent paper written by our three good friends, Dan Reed and Dennis Gannon, and none other than Jack Graf, which basically says there's a communication ACM article which says HPC forecast cloudy uncertain. And when you read the paper, there are like 5 points of concern or 5 recommendations. And I'll just give you a short version, from point 1 to point 4. Semiconductor change dictate new approaches, end-to-end hardware, software is essential, prototyping at scale required, space of leading edge HPC apps is far broader. Yeah, we cover all that, right, already in Fugaku and our feasibility study. We do this. One thing that's not evident is cloud economics have changed the supply chain ecosystem. And cloud companies now lead IT innovations even beyond chip vendors like Intel and NVIDIA. And also, they also say that compared to the government HPC investment, these corporate investment, the government HPC investment is dwarfed by that. And thus, there's a potential for clouds to subsume HPC as we know it, which seems like a bleak thing. And then they all go on to recommend that there'll be government funding to create something bespoke, which is bespoke architecture, which will not cover what the cloud space will cover. But is this the right approach? And this is where I just disagree with these my three good friends, because in the future HPC, and this is sort of already what we're practicing with Fugaku, is platform. And this is our strategy. It's weekend strategy now. Because the one who rules the platform rules the world. Okay. And this is pretty clear. And that's where all the DX, or digital transformation, that's what digital transformation is all about. So when you think of shopping, right? In the past, shopping, you had lots of retail stores in your neighborhood and stuff, and people ran around with their carts or cards, and the shopping knowledge confined to individual merchants and consumer. But with digital transformation, we know this all changed. We have the hardware, we have the IT platform, and hardware like Amazon Cloud or whatever cloud infrastructure. Then we have the storefronts, and then we have people shopping, we have the delivery infrastructure, and so forth. So people do online shopping. And why is like a company like Amazon or in Japan, Rakuten, why are they strong? Because all the knowledge pertaining to shopping is accumulated in the platform. Okay, this is where the business is. It's no longer people running around. It's all digitized. All the knowledge are encoded in terms of data, but not just data, algorithms, programs, trained neural networks. It's all accumulated and synthesized together in the platform. Same thing will happen to science. Right now, we have individual labs, and people write papers to disseminate information. It's so old school. Right? This is so old school. With digital transformation, the same thing will happen. Then we have a platform, digital platform. Then we have for each individual domain, like pharmaceutical, smart city, power grid, whatever. Right? We'll have essential digital platform where scientific knowledge will be encoded, again, in terms of data, in terms of digital twins involving data, algorithms, programmed, and trained neural networks. And who will control science? Just like a company like Amazon controls shopping. There's people who control the platform that will control the science. So if we are to build machines, this is what we have to aspire for. And we're doing that right now. Even with Fugaku, I'm sorry for the Japanese, we're building several platforms. This is a pharmaceutical platform. This man being led by a professor and our team leader, Okuno-san, that will try to digitize all the pharmaceutical development pipeline. And this is not just a piece of the pipeline, the entire process. But even parts of it, the downside is even parts of it will involve some like 55 software components, even that part. So when it completes, there'll be hundreds of components that need to interact, just like your cloud shopping site. There are hundreds of components involved making Amazon true. It's the same thing with any of these digital platforms. It's not just one big program that solves your problem. Okay? So again, one who rules the platform. So we really should get rid of the outdated HPC big iron mentality, like Zeta-scale machine on the 500 or whole machine big science run, fancy AI accelerator, developing chips to get like 10 times speed up, strong scaling, which is not inconsequential. We should invest in, and this is where it's really discreet, we should not invest in built for purpose systems, because that's not going to really help building the platform. Because we have to have hundreds of programs running on the platform. How are you going to certify any of them? How are you going to develop any of them? Okay. Rather, the platform applications now, the platform first strategy. And there, for us to lead, leadership and generality, not specialization. Leadership and generality is the key. Okay? And this is where the cloud vendors may not necessarily have the leadership. That is to say, applicable to wide-ranging applications. For example, how do we get 10 times leap in memory bandwidth? Nobody knows, right? How do we have alternative means of computation where important problems that require things beyond our normal scaling, how can quantum computing be applied? Again, platform software is so tremendously complex. There are hundreds of components involved in any of the scientific platforms, such that you cannot afford to create customized accelerator chips. That's a totally foolish thing to do. Rather, we should work with the industry to develop general purpose, what would really happen as a general purpose acceleration of the workloads, because these will span across multiple disciplines. Okay. And this is where our leadership should be. And this is exactly what we're doing right now. So what we're doing right now is with our cloud vendors, like Fujitsu's clouds that's adopting AC4FX directly. But of course, there are other vendors too, especially Amazon, who just developed the AWS Graviton3 processor and deploying these in Amazon EC2 instances. And these ISOs are highly compatible. So of course, we're trying to cloudify Fugaku. So a whole bunch of, we have already put cloud APIs on Fugaku. So it has, so it can interact with Amazon Cloud. But what's more important, when we sign an MOU in January, is to basically what we might call Fugakifying the cloud, or the virtual Fugaku. That is to basically implement application system software so that there will be a virtualized environment that would extend the platform that developed on Fugaku onto AWS. So then this will really help these platforms to be disseminated. The pharmaceutical platforms, smart city platforms, any platform we develop to be disseminated to the commercial industry space. And then, of course, there'll be hardware requirements. And when they're compatible, then they'll run across, right? Because these are compatible processors. And they have similar performance characteristics. And that's the important things. Okay, let me spend 1 or 2 minutes to say quantum computing. So again, this workload and analytics. We all know that there will be some quantum future, but there will be significant non-quantum future because most applications will not be able to utilize quantum speedup, but some do. Some important problems do. So there's been a recent problem by, again, our good friend Thorsten Hoffler and also Matthias Streuer, who is a very renowned physicist, looking at, okay, what's the real story about quantum speedup? Not what the physicists making these machines tell you, because they don't really know algorithms. Well, some do, but not many of them do. So the analysis says that Shor's algorithm is exponential. So it's good because their claim is that for any quantum algorithm to have real quantum supremacy, it has to have exponential speed up over existing algorithm. So something like Grover's algorithm, which is like a search algorithm, is not good. It will not be useful because it only has quadratic algorithm. So this will be published for CSCM. But we're nowhere near a situation where we can run any of these algorithms with exponential speed up to do something and that's something useful in reality. For example, there's another paper which says how much error correct how much qubits you need to break the RSA 2048 in reasonable time. But basically, when you read the paper and do your own analysis, you need about 200 million qubits, NISQ qubits. So right now, the biggest is like 100, a few hundred. So we're still far off from there. But it's not to say they're not useless. I mean, there are lots of new algorithms like hybrid algorithms, like variation algorithms, but really need to, again, conduct a scientific experiment. Because, for example, they have the investigation. For example, they have all this the analysis of like how many qubits versus how long it will take. And for things like quantum dynamics, it could become useful fairly soon. Things like quantum chemistry or factoring, you can say that some problems take a century to compute, even with planar qubits, but things may change. So we're working with the industry to implement a quantum platform, which we'll hope will be biggest platform compared to any other similar platform in the world, combining both real machines, multiple real machines, and quantum simulations on Fugaku and associated dedicated machines. And we're shooting for like 1,000 to 10,000 error-free quantum qubit simulations on simulators. And of course, we'll try to match that up against the real NISQ machines and have a comprehensive software for people to develop new algorithms such that we can know scientifically where and how quantum computing can be useful, not hyped. Okay, that's my final slide, and hope that found it useful. Hope you have a great rest of the week, and thank you very much for listening.